This lecture we studied about n-type and p-type semiconductors, and then after that we studied about the Fermi energy level for n-type and p-type semiconductor. In this chapter we will study the conductivity of semiconductor materials. Before going to conductivity, we will define two small quantities. Number one, electric field intensity. Consider a material. It may be an a metal or a semiconductor. If a supply is given to the material, a potential difference is created across the terminals of the material. A battery V is applied across the material. The charge carriers in the material starts moving. If the battery is applied across the material, the positively charged carrier hole move in this direction, and negatively charged carrier electron move in the opposite direction. When supply is given to the material, the charge carriers in the material move in the opposite direction. This motion basically happens due to a force which acts on the charge carriers when it is connected across the supply. Actually, it happens that when a supply is given across to the material, a field acts upon the material, and this field acts as if a force is applied on the charge carriers on the material. So I can define the electric field as it is the force which acts on the charge carriers when when supply is connected across the material. So electric field is basically a force which acts on the charge carriers when a potential difference is created across its terminal. Mathematically, this electric field is defined as E equal to minus dV by dx. Suppose here x equal to 0 and x equal to something. This is the length of material, and this is the length of material, and at this point on the material the potential is V, and as we go in this direction the potential decreases to 0. So between these two terminals the potential difference is V minus 0 equal to V. Means potential difference is applied across the material, then an electric field setups, and it due to this electric field the charge carriers move in the given direction. The negative sign in the electric field represents E decreases, sorry, negative sign represents voltage dV change is negative in the direction of electric field. We can see in the diagram, in the direction of electric field, if we move in the direction of electric field the potential decreases from 0 V to 0, from V to 0 potential decreases in the direction of electric field, hence this negative sign in the definition of electric field. So with the knowledge of change in voltage with respect to change in distance, we can calculate electric field in the material. But every time it is not possible without the data given to calculate electric field, because if I want to calculate electric field at this distance, at this point, I should know that if I move with distance dx, what is the change in voltage dV. If I know both the things, then electric field can be calculated as E equal to minus dV by dx. Suppose I have a material. In this material, the cross sectional area which may be circular or square shaped or rectangle shape, the cross sectional area and doping of the material are uniform. If the cross sectional area and doping are uniform, then the electric field at any point in the material will be same. That is, at this point electric field E1, at this point electric field E2, at this point electric field E3. If this material has cross sectional area uniform and doping uniform, then the electric field at any point in the material will be same, that is E1 equal to E2 equal to E3, and this can be calculated as the supply given to the material, total voltage applied, that is V, divided by length of the material, that is E equal to V by L, and unit of electric field is volts per meter or volts per centimeter. Another important thing we will study is mobility of charge carriers. Mobility of charge carriers. The mobility of charge carriers we will define by taking an example. Suppose these are two materials in which electric field is applied. Both the materials have same electric field E. I will write it here. Both the material have same electric field, same electric field, and in this material, uh, I taken a, I select the charge carriers, two charge carriers. If electric field is applied to the material, these two charge carriers will move in the material. I will note the velocities of these two charge carriers. This is V1, this is V2. And after comparing the velocities of the two charge carriers, uh, V2 is greater than V1. If V2 is greater than V1, then I can conclude that if same electric field is applied to both the material, then also this charge carrier is moving with a greater velocity than this charge carriers, then I can conclude that this particular charge carrier in this material can freely move in the material. That is, this charge carriers has mobility greater than this charge carrier. So I can define here mobility as it is it is the measure of how quickly charge carriers can move in the material. How quickly charge carriers can move in the material. We have taken two materials, same electric field is applied, then also the charge carrier in one material moves with greater velocity, then I can conclude that that charge carrier has greater mobility. Mobility is mathematically defined as mu equal to drift velocity per unit applied electric field. Electric field. Drift velocity will be represented with Vd and applied electric field will be represented with E. The unit for mobility is meter square per volt second or centimeter square per volt second. Here are some values of mobility at T equal to 300 degrees Kelvin, room temperature. At room temperature, mobility, some values of mobility: mu1, mu p. Mu1 whole mobility, sorry, mu1 electron mobility and mu p whole mobility. We will write the values of mobility for two materials, germanium and silicon. For germanium, mobility, electron mobility is 3800 centimeter square per volt second, and for holes it is 1800 centimeter square per volt second. For silicon, electron mobility is 1300 centimeter square per volt second, and it is 500 centimeter square per volt second for holes in silicon material. This was all about mobility of the charge carriers. Now we will define conductivity of the material. Conductivity is the measure of ability of the material to conduct. Conductivity basically depends on flow of charge carriers. Conductivity is defined as conductivity equal to charge of carrier into charge carrier concentration into electric field into mobility of into mobility of charge carriers. Conductivity is represented by sigma, and it can be written as charge of carrier. Charge of carrier, there will be two type of charge carriers, that is electron and hole. For both, the charge of carrier will be written as q. Second quantity, charge carrier concentration. Charge carrier concentration means electron and hole concentration. So then in the conductivity equation, the charge carrier concentration will be either p or n, and mobility of charge carrier will be either mu p or mu1. This is the equation for conductivity. Now we will define conductivity for different type of material. Conductivity has unit Siemens per meter or mho per meter. Now conductivity for intrinsic semiconductor. In case of intrinsic semiconductor, both electrons and holes take part in conduction. If both the type of charge carriers are taking part in conduction, conductivity is defined as n q mu n. This is conductivity due to electron plus p q mu p. This is conductivity due to holes. In case of intrinsic semiconductor, we know that n into p equal to ni. Then replacing n and p with ni, we can write sigma equal to ni into q into mu1 plus ni into q into mu p equal to ni into q into mu1 plus mu p, Siemens per meter or Siemens per centimeter. This is the conductivity equation for intrinsic semiconductor. It can be further simplified as Ni into Q into mu1 plus V. Oh, sorry, we have already simplified. Now we will see the temperature coefficient of conductivity. Conductivity depends on this Ni. First, we will discuss about Ni. Ni is intrinsic carrier concentration, and its equation we have already seen. Ni square equal to A naught into T cube into e raised to power minus Eg0 divided by kT. We can see that the intrinsic carrier concentration is directly proportional to temperature, so we can conclude that Ni increases with temperature. If temperature is increasing, Ni will increase. Number 2, mobility. Charge of carrier will be always constant, but mobility of charge carrier is affected by the temperature. Simply keep one thing in mind that if temperature increases, the mobility of charge carriers mu1 or mu p decreases. This decrement is because in the material, if these are the atoms and these are the charge carriers which are moving, then with increase in temperature these atoms starts vibrating. With the vibration, the chances of collision between these charge carriers and atoms is increases, and the chances of collision increases, and due to these collisions the velocity of the charge carrier decreases, that is Vd decreases with temperature, and if Vd decreases, mobility decreases. So we will keep this thing in mind that mobility of charge carriers decreases with the temperature. Here the conductivity depends on Ni and mu1 both. Mu1 mu decreases with temperature while Ni increases with temperature, but practically it has been proved that due to the decrement in mobility due to decrement in mu1 and mu p is very less as compared to increment in conductivity due to increment in Ni. So finally I can conclude that sigma conductivity of intrinsic semiconductor with temperature increases with temperature, that is sigma for intrinsic semiconductor has positive coefficient of temperature. Now we will define conductivity for n-type semiconductor. In case of n-type semiconductor, again both the type of charge carriers take part in conduction. So conductivity here can be defined as sigma equal to nq mu1 plus pq mu p. This is conductivity due to holes. This is conductivity due to electron. As electrons are majority charge carriers and electron concentration is very greater than p, hole concentration is very less than n. So I can say that this part of conductivity equation is very less as compared to this part. So I can neglect this part. Sigma can be written as sigma is nearly equal to nq mu1. In this conductivity equation, N can be replaced for N-type semiconductor as Nd. So I can write conductivity equation sigma is equal to Nd into Q into mu n, Siemens per meter or Siemens per centimeter. This is the conductivity equation for N-type semiconductor. Number 3, P-type semiconductor. Again, in p-type semiconductor, both the type of charge carriers will take part in conduction, and conductivity will be defined as sigma equal to nq mu1 plus pq mu p. But in p-type semiconductor, the hole concentration is very greater than electron concentration, so I can neglect this part of conductivity due to electrons, and conductivity can be written as sigma is nearly equal to pq mu p. And in p-type semiconductor, p is nearly equal to Na, and conductivity sigma is nearly equal to Na into q into mu p. These are the conductivity equation for n-type and p-type semiconductor. Now we will see the temperature coefficient for n-type and p-type semiconductor. Let's take an example of n-type and p-type semiconductor. First, in intrinsic semiconductor, for example, n equal to p equal to 10 raised to power 10. Then according to mass action law, n into p equal to 10 raised to power 10 into 10 raised to power 10 equal to 10 raised to power 10 into 10 raised to power 10 equal to 10 raised to power 20. And if we add the total number of charge carrier in intrinsic semiconductor, then n plus p equal to 10 raised to power 10 plus 10 raised to power 10 equal to 2 into 10 raised to power 10. In case of n-type semiconductor, for example, I take n equal to 10 raised to power 15 and n equal to 10 raised to power 5, then n into p equal to 10 raised to power 15 into 10 raised to power 5 equal to 10 raised to power 20. According to mass action law, both the values are same. We have changed the composition, but we have kept the material at thermal equilibrium, and according to mass action law, the product of electron and hole concentration is same in both the cases. Now if we add the total number of charge carriers, then n plus p equal to 10 raised to power 15 plus 10 raised to power 5 is nearly equal to 10 raised to power 15, which is very greater than 10 raised to power 15 is very greater than 10 raised to power 10, as this much difference is there in the total charge carrier concentration in extrinsic semiconductor and intrinsic semiconductor. So I can conclude that the total number of charge carriers in extrinsic semiconductor n type or p type is far greater than the total number of charge carriers in intrinsic semiconductor. So with increase in temperature, more number of charge carriers will be generated, and uh, already we have seen that the charge carrier concentration is very large in extrinsic semiconductor. So I can say that with this much concentration of majority charge carriers in extrinsic semiconductor, it is become very difficult for majority carriers to move in the material and mobility is badly affected by the temperature. Hence finally we can conclude that in n-type or p-type material, conductivity decreases with temperature. That is, conductivity of n-type and p-type has negative coefficient of temperature. Negative coefficient of temperature. Now we will define resistivity of the material. Resistivity, written as rho, is the reciprocal of conductivity. Means resistivity is the reciprocal of conductivity. If we know the equation for conductivity for all the materials, then we can also calculate its resistivity. First, for intrinsic semiconductor, sigma equal to Ni into Q into mu1 plus mu p. So its resistivity will be defined as rho equal to 1 upon Ni into Q into mu1 plus mu p. Conductivity of intrinsic semiconductor increases with temperature. Temperature increases, conductivity increases. If conductivity of intrinsic semiconductor increases, then resistivity decreases with temperature. Means resistivity of intrinsic semiconductor has negative coefficient of temperature. Number 2, N-type semiconductor. For N-type semiconductor, conductivity is defined as sigma is equal to Nd into Q into mu1. If conductivity equal to Nd into Q into mu1, then the resistivity will be equal to 1 upon Nd into Q into mu1. For N-type semiconductor with increase in temperature, conductivity decreases, then resistivity increases. Means resistivity of N-type semiconductor has positive coefficient of temperature. Number 3, P-type semiconductor. In case of P-type semiconductor, conductivity is defined as sigma equal to Na into Q into mu p. If conductivity is equal to Na into Q into mu p, then resistivity will be reciprocal of this 1 upon Na into Q into mu p. With increase in temperature, conductivity of P-type semiconductor decreases, hence resistivity increases. Now, resistance of the material. Resistance. Resistance is defined as R equal to rho L by A. For example, this is the material for which we are calculating resistance. For this material, its cross-sectional area will be A. This is cross-sectional area. And this will be the length of material L. And this rho will be resistivity of the material. We know the equation of resistivity for intrinsic N-type and P-type semiconductor. So calculating the resistance for different type of material will not be much difficult if we know the equation for resistivity. Also, the unit for resistance is ohms. If the unit for resistance is ohms, so I can write from here resistivity rho equal to R into A by L. Means ohm into meter square by meter equal to ohm meter. From here I can define the unit of resistivity equal to ohm meter or ohm centimeter. Next, conductance. Conductance of the material is written as G, and it is the reciprocal of resistance of the material. The unit for resistance is ohms, then unit for conductance will be ohms or Siemens. Yes. We know that R equal to rho L by A. From this equation, uh, G can be written as 1 upon rho L by A. It can be written as A into sigma divided by L, where 1 by rho equal to sigma conductivity and unit is Siemens or mho. This is the conductance of the material. If we know conductivity of a material, then we can calculate its conductance. Now we will solve a problem on related to conductivity conductance. Given data is all electron mobility ratio equal to 0.4, doping concentration equal to 4.2 into 10 raised to power 8, sorry, into 10 raised to power 8 atoms per meter cube. Intrinsic concentration equal to 1.5 into 10 raised to power 4 atoms per meter cube. Calculate the ratio of conductance of n-type semiconductor to the conductance of intrinsic semiconductor. The material is n-type semiconductor. It is given in the problem. This question was asked in GATE 2006 electronics paper. We know that conductance of a material is equal to 1 by resistance, and resistance equal to rho L by and resistance R equal to rho L by A. From this equation we can write as conductance equal to sigma A to A divided by L. Now for n-type semiconductor, conductivity is defined as sigma n equal to Nd into Q into mu n, and for intrinsic semiconductor, conductivity is defined as sigma I equal to Ni into Q into mu n plus mu p. Putting the corresponding values, we can calculate the conductivity for n-type and p-type semiconductor, n-type and intrinsic semiconductor. But in the given problem, conductivity is not given directly, but a ratio of electron to hole mobility mu p upon mu n is equal to 0.4 is given. Now the ratio can be found out as Gn upon Gi is equal to Nd into Q into mu n upon Na into upon Ni into Q into mu n plus mu p. Q cancels out and value of Nd is given as 4.2 into 10 raised to power 8 divided by Ni is given as 1.5 into 10 raised to power 4, and mu n and mu p are not given, so we can write this as 1 upon mu n plus mu p divided by mu n divided by mu n. So we can write it as 4.2 into 10 raised to power 8 divided by 1.5 into 10 raised to power 4 into 1 upon 1 plus 0.4. Solving this, we get gn upon gi equal to 20,000, which was in option. Gn upon gi equal to 20,000. Now we will study about drift and diffusion mechanism. Drift mechanism. Suppose there is a material. In this material, if we apply a battery across it, then due to application of this supply, an electric field will act on this charge carriers, and due to this electric field, holes move in the direction of electric field and electrons will move in the opposite direction of electric field. This motion of charge carriers due to applied electric field is called drift motion. So I can define drift mechanism as motion of charge carriers under the effect of applied 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 electric field under the effect of applied electric field is called drift motion, and the velocity of charge carriers due to drift motion is defined as Vd, drift velocity. Means we can now say that drift motion is possible only if we have an electric field applied across the material. Another mechanism of charge carrier motion is diffusion. Suppose we have a material. In this material, we are looking at this cross section, and to the left hand side of this cross section, this is the charge carrier concentration. Here, for example, I have taken electrons, and to the right hand side of this cross section, this is the charge carrier concentration. By observation, it can be clearly seen that the electron concentration on this side is far greater than the electron concentration on this side. If we move with a very small distance dx from this point to this point, there is change in electron concentration dn. Means in this material at this cross section point, there exists a change in electron concentration with respect to change in distance, and this ratio is called concentration gradient. It is called concentration gradient. If in a material there exists a concentration gradient, then the charge carriers have tendency to move from higher concentration to lower concentration, and this motion of charge carriers from higher concentration to lower concentration is nothing but diffusion of charge carriers. As the charge carriers move forward, diffusion starts decreasing, and i I can say that diffusion will die out where the concentration of electron in the material will be uniform. From this point diffusion starts, and at this point the diffusion ends. This is called L diffusion length. Here many charge carriers come forward, and after some time the concentration will be little bit higher here, and now the difference in the carrier concentration at this point will be less as compared to this difference dn with this dx. So the diffusion uh, continuously decreases, and one point when the total concentration of electron in the material becomes uniform, at this point the diffusion will die out, and this starting point to end point, this length is called diffusion length, and this diffusion length is defined as L equal to under root of d into tau, where d is called diffusion constant and tau is called minority carrier lifetime. So in drift mechanism, due to application of electric field, charge carriers move, while in diffusion without an electric field, charge carriers move from higher concentration to lower concentration. Now we will define current density. Suppose this is a material. In this material, if charge carriers move from one side to other side, if I observe the charge carriers, then for this small time dt I have observed the charge carriers. These charge carriers moves from this point to this point, means there is a change in charge with respect to change in time, and if there is change in charge with respect to change in time, so I can say that this material is conducting, means current is flowing through the material. Current is nothing but change in charge with respect to change in time. In semiconductors, when the charge carriers will move, there will be change in charge with respect to change in time, and we will define the current in the semiconductor. But we have already seen that in semiconductor, charge carriers move due to two mechanisms: number one, drift mechanism, and number two, diffusion mechanism. In drift mechanism, we have applied electric field, and due to this electric field the charge carriers move, while in diffusion there is motion of charge carriers due to change in concentration, or if concentration gradient dn by dx or dp by dx exists in the material, then the charge carriers will move from higher concentration to lower concentration. As there are two type of motions in of the charge carriers, we will define two current densities. Number one, drift current density. Drift current density. Drift current density is due to the motion of charge carriers due to drift mechanism, and this drift current density is defined as J drift equal to sigma into E applied electric field. Conductivity, sigma is called conductivity, and we know the equation of this conductivity for different material, and this E is applied electric field. Unit of current density is ampere per meter square. Ampere. Ampere per meter square or amperes per centimeter square. For different type of material, the conductivity equation can be obtained by putting different values of sigma. Number 2. Diffusion current density. Diffusion current density is due to motion of charge carriers uh, due to existence of concentration gradient. Diffusion current density is defined for electrons and holes both separately. For electrons, diffusion current density is defined as Jn diffusion is equal to dn into q into dn by dx. And for holes, this diffusion current density is defined as Jp diffusion equal to dp into q into dp by dx, where q is charge of carriers and its value is 1.6 into 10 raised to power minus 19 coulomb. Sorry, this diffusion current density is equal to Jp equal to minus dp into q into dp by dx, and dn by dx or dp by dx is called concentration gradient, and dn is called electron diffusion constant, and dp is defined as hole diffusion constant, electron diffusion constant and hole diffusion constant. This is the current density in the material. Now we will solve some more problems on basic semiconductors. A silicon sample A doped with 10 raised to power 18 doped with 10 raised to power 18 atoms per centimeter cube of boron, and another sample B of identical dimension is doped with 10 raised to power 18 atoms per centimeter cube of phosphorus. Calculate, sorry, electron to hole mobility means mu n by mu p equal to 3. Calculate the ratio of conductivity of sample A to conductivity of sample P. This question was asked in GATE 2005. Sample A In sample A, boron was added. If boron was added, sample A is p-type semiconductor. In sample B, phosphorus was added, and with the addition of phosphorus, the sample B will be n-type semiconductor. Conductivity of sample A to conductivity of sample B will be conductivity of p-type semiconductor to conductivity of n-type semiconductor, which is written as Na into Q into mu n upon Na Nd into Q into mu p, which will be 10 raised to power 18 by 10 raised to power 18 into mu n upon mu p. Sorry, this will be mu p and this will be mu n. This will be mu n, and this ratio will be mu p upon mu n. This will cancel out, and the ratio mu n upon mu p is given as 3. Then mu p upon mu n will be 1 by 3. Next question. The intrinsic carrier concentration of silicon at 300 degrees Kelvin is 1.5 into 10 raised to power 16 per meter cube. If after doping the number of majority carriers are 5 into 10 raised to power 20 per meter cube, the minority carrier density is. This question was asked in GATE 2003. Here we are given with intrinsic carrier concentration Ni equal to 1.5 into 10 raised to power 16 per meter cube. If the semiconductor is doped, the majority carrier concentration is given as majority concentration is equal to 5 into 10 raised to power 20, and we are asked to calculate minority carrier density. We know that according to mass action law, majority carrier density or carrier concentration into minority carrier concentration, majority carrier concentration into minority carrier concentration equal to Ni square. Using this mass action law, we can calculate minority carrier concentration as minority carrier concentration will be equal to Ni square by majority carrier concentration. Majority carrier concentration. Ni is given as 1.5 into 10 raised to power 16, and its square will be taken, and majority carrier concentration is given as 5 into 10 raised to power 20. This will come out around 4.50 into 10 raised to power 11 per meter cube. Let's solve one more problem on basic semiconductors. the concentration of electron in a sample of uniformly doped n-type silicon at 300 degrees Kelvin varies linearly from 10 raised to power 17 per centimeter cube at x equal to 0 to 6 into 10 raised to power 16 per centimeter cube at x equal to 2 micrometers. If electronic charge is 1.6 into 10 raised to power minus 19 coulomb and diffusion constant dn equal to 35 centimeter square per second, the current density in silicon, if no electric field present, is. So in this problem we are given concentration of electron at x equal to 0 and concentration of electron at x equal to 2 micrometer, and diffusion constant is given. We are to calculate the current density in the semiconductor material if no electric field is present. We already know that the current density is due to two mechanisms, one due to drift mechanism and one due to diffusion mechanism. Here electric field intensity is 0, so we can conclude that J drift will be equal to 0. There will be no drift current density, but there will be diffusion current density, and we have to calculate that diffusion current density. In this material we take 2 point x equal to 0 micrometer and x equal to 2 micrometer. At this point the carrier concentration is 10 raised to power 17 per centimeter cube, and at this point it is 6 into 10 raised to power 16 per centimeter cube. If we want to calculate diffusion current density due to electrons J and diffusion, its equation is given by dn into q into dn by dx. Q is given, dn is given, dn by dx we have to calculate. This is called concentration gradient. We have to calculate this concentration gradient. Concentration gradient dn by dx can be calculated as change in electron concentration with respect to change in distance equal to n2 minus n1 upon x2 minus x1. For example, I take this point as 1 and this point as 2. So n2 equal to 6 into 10 raised to power 16 minus n1 equal to 10 raised to power 17 divided by x2, 2 micrometers and minus 0 micrometer. The unit of this concentration is per centimeter cube, while the unit is micrometer in the denominator. So we will have to change the unit of denominator. First we will calculate the numerator part, and it will come out minus 4 into 10 raised to power 16. Minus 4 into 10 raised to power 16 divided by 2 into 10 raised to power minus 6 meter into 10 raised to power 2 centimeter. So it will be minus 4 into 10 raised to power 16 divided by 2 into 10 raised to power minus 4 centimeter, and this will be per centimeter cube, and this will come out to be minus 2 into 10 raised to power 20 per cent cube. We have calculated the dn by dx. dn by dx is minus 2 into 10 raised to power 20. Now the current density can be calculated as Jn diffusion will be equal to dn into q into dn by dx, and this will be 35 into 1.6 into 10 raised to power minus 19 into minus 2 into 10 raised to power 20. This will be, and after calculating this will come out as minus 1120 ampere per centimeter square. Negative electric field and negative current density means negative sign represents uh, electrons move from x2 to x1. Electrons move from x2 to x1, but current flows in the opposite direction. This is flow of electron, diffusion direction of electron, and this is direction of current. So electric field will be negative due to electrons.